Right now, somewhere on your face, there's a muscle that has absolutely no job. It sits just under the skin of your upper lip. It's been there your entire life. Most scientists think it will eventually disappear from the human body completely. It's the last physical remnant of a sensory system that every other mammal on Earth still uses, and that your ancestors lost roughly 800,000 years ago. Humans lost the DNA for whiskers around 800,000 years ago, and what's wild about that number is that it isn't a guess. It's not somewhere in the distant past. Researchers can actually pinpoint the window in the human genome where the switch got flipped. You can look at the timeline of human evolution and point to a specific era and say, that's when it happened. And when you understand what whiskers actually are, what they can do, and why losing them may have been one of the most consequential trades our lineage ever made, the story gets a lot more interesting than just we lost some hair. So here's what this video is. We're going to trace exactly what whiskers are, why they're far more powerful than most people realize, what happened in the human genome to shut them off, what we gave up, and what we got in return. And there's one part of this story near the end that almost nobody talks about. It's something that connects whisker loss directly to the shape of your brain right now. Keep that in mind as we go through this. Let's start with what a whisker actually is, because most people think of it as just a long, stiff hair. It is not. Whiskers are vibrissae, keratin filaments that grow out of different follicles than regular hair. Those follicles are much deeper and are surrounded by pockets of blood that amplify vibrations to better communicate information to the nerve cells beside them. So before a signal even reaches a nerve, it's already been physically amplified by a blood-filled sinus wrapped around the base of the hair. And a single one of those follicles can contain over 1,000 nerve endings. That's more sensory wiring than almost any other patch of skin on an animal's body. This isn't hair. It's closer to an organ that happens to grow out of the face. And here's something most people don't know. Macrovibrissae are motile and used for distance detecting and object locating, while microvibrissae are immotile and used for object identification. So most mammals are running two separate whisker systems simultaneously. One for sweeping the environment at a distance, and one for figuring out exactly what they just touched. They're not redundant, they do completely different jobs. Now rodents take this even further. They don't just passively wait for something to touch their whiskers, they actively sweep them back and forth at 5 to 25 times per second in a motion called whisking. This is driven by a rhythm generator in the brainstem that keeps firing even with no sensory input at all. It's not a reflex, it's more like a built-in scanning mechanism. The animal is constantly reaching out into the world with its face, building a real-time picture of everything around it. But the most extreme version of this, the one that genuinely seems impossible until you see the research, is what seals can do. Marine mammals often forage in dark or turbid waters, while dolphins use echolocation under such conditions. Pinnipeds apparently lack this ability. For seals hunting in the dark, one source of sensory information may consist of fish-generated water movements, which seals can detect with their highly sensitive whiskers. Water movements in the wake of fishes persist for several minutes, so a fish swims through the water, leaves a wake, and swims away. The disturbance it created lingers in the water long enough for a seal to find it, read it, and figure out which direction the fish went. Blindfolded seals can use their whiskers to detect and accurately follow hydrodynamic trails generated by a miniature submarine. Not just detect the trail, follow it accurately, in the dark, with no vision, no sound, just whiskers reading the ghost of a movement that already happened. And to pull that off, the seal's whisker system has to solve a problem that sounds almost impossible. It has to filter out the turbulence created by the seal's own swimming in real time. Otherwise, its own movement would completely drown out the faint signal it's trying to read. The whiskers have a specific undulating shape, not smooth like you'd expect, that suppresses the vibrations caused by the seal's own body cutting through the water. It's essentially active noise cancellation built into the geometry of the hair itself. Researchers studying this wanted to uncover how the basic physics of fluid flow around the whiskers enables them to sense their environment, and to use what they discovered to engineer a new technology. A flow sensor that can track a fading hydrodynamic trail which installed on autonomous underwater vehicles would improve their ability to navigate. We are literally reverse engineering whiskers to build underwater robots. That's how sophisticated this system is. So that's what whiskers can do at their peak. Now here's where the human story gets specific. Whiskers underwent a reduction throughout the primate adaptive radiation and disappeared completely in the human lineage. Yet vestiges of whisker capsular skeletal muscles remain in the human upper lip. That muscle at the top of this video, the one with no function, is the exact muscle that once moved whiskers voluntarily in your ancestors. The follicles are gone, the sensing is gone, but the muscle that would have aimed them is still there waiting for a job it will never have again. The question is, what actually turned them off? And this is where the science gets genuinely fascinating because it's not a slow fade. It's closer to a gene getting unplugged. A gene called PRDM1 plays a crucial role during whisker development. PRDM1 conditional knockout mice are one of the very rare transgenic animals entirely lacking whisker follicles, while pelage hair follicles develop normally. So knock out this one gene in a mouse and you get an animal with a full coat of body hair and a completely bare face where the whiskers should be. PRDM1 is essentially the master switch for whisker construction. Now, researchers have demonstrated that a gene called LEF1 acts upstream of PRDM1 and have identified a primate-specific deletion of a LEF1 enhancer. This loss may have been significant in the evolutionary process leading to the progressive defunctionalization and disappearance of vibrissae in primates. So the chain looks like this. The enhancer that turns on LEF1, which in turn activates PRDM1, which builds whisker follicles. That enhancer got deleted in the primate lineage. Pull one piece out of the chain and the whole downstream process never starts. The follicles don't form. The whiskers don't grow. And based on genomic comparisons, that deletion traces back roughly 800,000 years in the human line. Here's what makes this even more interesting. Not every primate went the same direction. The primates that stayed nocturnal, that moved slowly through dense brush, lemurs, tarsiers, kept prominent functional whiskers. The primates that leaned hard into daylight vision and complex hand movement, the lineage that eventually became us, are the ones where whiskers all but vanished. The loss of regulatory elements in genes might explain the morphogenetic changes that occurred throughout the primate adaptive radiation. This led to the reduction in snout size and vibrissae while hands and eyes of diurnal primates took over as sensory organs. So this wasn't inevitable. It was a fork in the road. Different primate branches made different trades. Our branch traded the whiskers. Now here's the part I mentioned at the start, the part that connects all of this directly to the shape of your brain right now, and why losing whiskers might have been less of a loss and more of a reallocation. In animals with heavy whisker use, a large section of the sensory brain called the barrel cortex is devoted entirely to processing whisker signals. Individual neurons are mapped one-to-one to individual whiskers. It's a dedicated whisker map, and it takes up serious neural real estate. Genetic ablation experiments have confirmed that the absence of motile macrovibrissae reverberates on the organization of nerve wiring in the mystacial pads, and on the organization of the barrel cortex. When the whiskers go, the map reorganizes. The reorganization of the somatosensory cortex is a phenomenon of great evolutionary importance given the expansion of the brain areas dedicated to the processing of sensory organs. And in primates, the sensory organs that expanded were the eyes and the hands. Humans have now largely integrated the function performed by whiskers into their brains, specifically into their somatosensory cortex. The human brain devotes relatively huge portions of itself to sensing and processing touch. Not face touch, hand touch, fingertip touch. The resolution we lost on our faces we rebuilt in our hands, and then some. So when you feel the difference between two surfaces with your fingertips, or when you can thread a needle or feel a splinter, you can't see. You're using sensory hardware that may have been partly funded by the same neural budget that once ran a whisker map. The trade wasn't random. It tracked exactly where our lineage was putting its evolutionary bets. On vision, on tools, on hands that could build things, and faces that could communicate. Which brings you back to that muscle in your upper lip. Vestiges of whisker capsular skeletal muscles remain in the human upper lip, sitting there doing nothing, slowly heading toward obsolescence. It's a timestamp, a record of a version of you that scanned the world with its face, that could read the air for movement, that had a scanning system built into its nervous system. That version of you gave all of that up around 800,000 years ago. And what it got in return is the brain you're using right now to understand why.